Okay, great. Okay. Thank you. So today we are very happy to have Li Yu from Max Planck in this giving a talk in this global Poisson. So he will talk about wonderful compactification of a Cartan subalgebra of a semisimple Lie algebra. Yeah, Li Yu, please.
Okay, thank you. Thanks a lot for the invitation and also for the introduction. It's my great pleasure to give this talk here. Yeah, as said, the title of my talk is Wonderful Compactification of a Cartan subalgebra of a semisimple Lie algebra. This is joint work with Sam Evans. And before I start, I should mention that last year I learned that there's this group of 5 people who wrote a paper on a combinatorial problem in which they introduced a variety which they called the Schubert variety, which turns out to be the same as our wonderful compactification. Okay, so the plan for today is as follows. So I'll start by defining what the wonderful compactification of a Cartan is as quickly as possible. And after this definition, I'll give you some motivations, basically to justify why this variety deserves to be called the wonderful compactification and why Poisson geometers should care about them. And then in section 2, I'll give you 2 examples that we all should keep in mind. And we'll refer back to these examples over and over again in this talk. And then in section 3, I'll discuss some algebraic geometric properties of this variety of the wonderful compactification, which I'll call H bar. For example, I'll show that it's a normal variety. I'll count the number of irreducible components in the boundary. I'll maybe also briefly discuss additive toric varieties. And then in the last section, I'll focus on the cohomological properties of H bar. So I'll compute the Betti numbers and also explain the multiplicative structure of the cohomology ring. And if time permits, I'll maybe also discuss the representation of the Bell group on the cohomology and some related problems. Okay, so to start, I'll always work over the complex numbers. G, as usual, is a semisimple group of adjoint type. H is a fixed Cartan subgroup. And the mass frac G and H are the algebras. Small n here in this talk denotes the dimension of G. G star is usually the dual space. And then we have the Grassmannian of n-dimensional subspaces of G semi-direct product G star. Sorry, I mean, for now, I guess you only need to think of the semi-direct product just as a direct sum of vector spaces. Okay, and then we have an embedding of G star into the Grassmannian by sending a linear functional alpha to all pairs y, negative coadjoint of y on alpha. In other words, if you wish, you can say that this is a graph of the coadjoint action of alpha on G. Okay, now what I can do is to take the closure of the image of G star inside the Grassmannian. And this closure is called the wonderful compactification of G star, and it's denoted by G star bar. Okay, this is a fairly simple definition. And then if kappa is my killing form, I can embed the Cartan subalgebra into G star by sending an element x of the Cartan into kappa of x comma blank. Okay, so then I have a composition of 2 embeddings. So H goes into G star, and then G star goes into the Grassmannian. So I can take the closure of H inside the Grassmannian. And then this closure is denoted by H bar, and it's called the wonderful compactification of H. Okay, these are simple definitions. Are there any questions so far? Okay, great. All right, so why are they called wonderful compactifications, and why do we care about them? Yeah, I mean, everyone is supposed to be a Poisson geometer, so we're all familiar with these. So I'll be very sketchy. So in general, if you have a Poisson group U comma pi U, then the infinitesimal information at the origin, at the identity element, is encoded in the Manin triple. In particular, we have the Stringfeld double Lie algebra and two Lagrangian subalgebras of the Stringfeld double. And then we can define the variety L of Lagrangian subalgebras of the Stringfeld double. So by definition, we have two particular points of this L, namely the point U and U star. Okay, so this variety has many nice properties. For example, it's a projective variety and is sitting inside the Grassmannian of d mu dimensional vector subspaces of the Stringfeld double. And moreover, if I'm given a Poisson homogeneous space M comma pi M, then we have the so-called Stringfeld map, sending M to the variety of Lagrangian subalgebras. It is known that this map is U equivariant, and you can there exists a Poisson structure on the variety of Lagrangian subalgebras such that this map is Poisson, and up to a covering map, this is embedding. So philosophically, one should think of the variety of Lagrangian subalgebras as the universal Poisson homogeneous space for the Poisson Lie group U comma pi U. Okay, therefore, it is natural and desirable to understand, for example, the Poisson geometric and the algebraic geometric properties of the variety of Lagrangian subalgebras. For example, one could ask, what are the symplectic leaves? What are the orbits of the Stringfeld double group? Or what are the orbits of U, etc., etc. Okay, for one instance of a Poisson Lie group, everything one wants to know about the variety of Lagrangian subalgebras has been completely worked out by Evans and Lu. This is what I call important case A. So what happens is you take G, equip it with the standard Poisson structure. Then the Manin triple is as written. Then I have the variety of Lagrangian subalgebras L of G direct sum G inside this variety of Lagrangian subalgebras. I have the diagonal G, which is one of the two subalgebras in the Manin triple. What I can do is I can compute the stabilizer inside the Stringfeld double group of this point, which turns out to be the diagonal G. So the orbit through this chosen base point of the Stringfeld double group can be identified with G cross G modulo the diagonal G, which can further be identified with G itself. Okay, and then if you take the closure of this orbit inside the variety of Lagrangian subalgebras, or equivalently inside the Grassmannian, what you get is the Concini and Procesi compactification of the group G. Okay, one of the reasons that the wonderful compactification G bar is important is the following result due to Evans and Lu. So if you take a G cross G orbit inside the variety of Lagrangian subalgebras, and then you take its closure. What is that? It turns out to be a fibration over a product of partial flag varieties, and the fiber turns out to be the wonderful compactification of some semisimple group. Okay, so in other words, if we pretend that we understand partial flag varieties relatively well, then to understand closure of G cross G orbits, we should start by understanding wonderful compactifications. Okay, now in this case, I can embed the Cartan subgroup H. Well, I mean, the Cartan subgroup H is a subvariety of G. As I said, G is now identified with an orbit of the Drinfeld double group, which sits inside the variety of Lagrangian subalgebras. So then I can take the closure of H inside the variety of Lagrangian subalgebras, or equivalently inside the Grassmannian. This closure, this H bar, is a toric variety, is in a sense the prototypical example of toric varieties. I mean, we know that each toric variety corresponds to a set of combinatorial data, which is called a fan. So just a collection or finite collection of cones such that the face of each cone is a cone and the intersection of two cones is also a cone. And we know that the combinatorial data corresponding to this H bar is the bell chambers, by which I mean the maximal cones of the span are the bell chambers. Okay, this is important case A, and then there's also important case B, which is supposed to be parallel to important case A. So what this is I take G star and I equip it with addition. So the group multiplication here is addition. Now on this algebraic group, I can equip it with the Kirchhoff-Poisson structure. It's well known that this is a Poissonian group, and its spanning triple is as written. Okay, and then you have probably noticed that I have written some letters in blue. So these things in blue are supposed to be so these are copied from important case A, and whenever you see something in blue, they are supposed to be analogs of whatever I write in important case B. Okay. All right. Then we also have the variety L of Lagrangian subalgebras, and then in this case, what I can do is I can take the point G, I mean the Lagrangian subalgebra G of the Drinfeld double, thought of as a point of the variety of Lagrangian subalgebras, which is analog of the diagonal G that we saw in important case A. And then we can compute the stabilizer in the Drinfeld double group G semi-direct product G star, and the stabilizer turns out to be G. So the orbit through the chosen base point of the Drinfeld double group can be identified via some computation, can be identified with G star via the map I wrote here. Okay, and then you can do some easy computation. You will realize that this composition map sends an element alpha of G star into this line, into this Lagrangian subalgebra. Okay, and what is that? This is exactly the definition that we started with at the very beginning. Okay, let me show you. It's exactly this. Okay, y comma negative coadjoint of y on alpha. Here also y comma negative coadjoint y on alpha. Okay, so this tells me that what I defined at the very beginning is the same as the closure of the orbit of the Drinfeld double group through the chosen base point G.
So in case A, you had that all the closures are smooth. Is this still the case here?
In that, most likely it's not the case.
So not exactly known, but
I mean, I'm pretty sure it's not the case, but I mean, I just haven't worked out the details. Yeah. Right. Yeah. I mean, for example, I don't think this G star bar is smooth. Yeah, and it could be very singular as far as I understand. Yeah. Okay. Right. So that's why we care about this G star bar. And then, as you can easily imagine, the H bar I defined at the beginning is supposed to be an analog of the toric H bar that we usually see in toric geometry. Okay, great. Any questions so far? Okay, nice.
but the H bar is smooth?
No, no.
Also.
I'll explain this later. It's not smooth. Okay. All right. Okay. So then we move on to section 2. So I'll give you 2 examples, the simplest possible examples. But for that, I'll need to introduce some notations. So phi is the set of all roots, phi plus minus the positive and negative roots, pi the set of simple roots. For each root lambda, I'll choose a root vector e lambda. And for simplicity, I'll identify G star with G using the Killing form. And then under this identification, so the composition map from H to the Grassmannian of n-dimensional subspaces of G direct sum G. I mean, G direct sum G as a vector space is just this G semi-direct product G star, but I only care about the vector space structure at this point. Some easy computation shows you that this composition map sends an element x of H to this last line here. Okay. I won't go through the details. I'm asking you to trust me that this computation is correct. And then the point is what? The point is, so here the first element, H direct sum 0. Oh, sorry, maybe I should have said that everything here sits inside our G direct sum G. Yeah, so the point here is that the first element, H direct sum 0, has nothing to do with X. Okay, it doesn't depend on X. So we don't care about that. And then in the second segment, the span of certain things. So it's a span of what? The span of E lambda, the root vector E lambda, comma, some complex number. So the root lambda applied to this element X of H times E lambda. And these vectors, everything comes with a negative sign. Okay, so the point is that to remember the image of X, one needs only remember these lambda X. Okay, once you know lambda X, you of course know negative lambda X. And once you know all the lambda X, you know the image of X. Okay, so what this computation buys me is the following commutative diagram. It's the following commutative diagram here. So the map from H to the Grassmannian factors through a map from H to this thing, C to the phi plus, where C to the phi plus stands for a vector space whose dimension is the same as the cardinality of phi plus. So a vector space whose dimension is the number of positive roots. Okay, and what is this map? This map just sends an element x of h to the tuple lambda x that we said we need to remember. Okay, and the map from C to the phi plus to the Grassmannian, of course, just sends a tuple x lambda to what we wrote. So h direct sum 0 plus the span of e lambda x lambda e lambda and e negative lambda negative x lambda e negative lambda as above. Okay, and then it's very easy to convince yourself that if I compactify C to the phi plus to P1 to the phi plus by compactifying each coordinate C to a P1, then this map from C to the phi plus to the Grassmannian factors through P1 to the phi plus. Okay, so what you do is so suppose you have a x lambda 0, x lambda 1 in homogeneous coordinates. I guess you just send this to h direct sum 0 plus the span of I guess x lambda 0 times e lambda x lambda 1 times e lambda. And then for the negative, you do the same. Okay. Yeah, this is easy, but the consequence is important. So the consequence is that so of course it's easy to show that this map from P1 to the phi plus to the Grassmannian is a close embedding. So to compute the closure of H inside the Grassmannian, what we could do is we first embed H inside this power of P1 and compute the closure of H there. Okay, are there any questions? Okay, nice. So examples. I guess the simplest possible example is type A1, in which case the set phi plus consists of one single element. There's only one positive root. So C to the phi plus is just C to the first power. Okay, so H, oh, sorry. So H to C to the phi plus is H to H goes to C. And of course, this is
Lee, can I ask a question?
Of course.
Yeah. So you could just start with just embedding everything to the P1 to the power 5 plus without going through any. So those could be just motivation, right?
Exactly. And this is
so eventually you forget about this Lagrangian subalgebra and any of that. Just start from
exactly. Yeah.
Oh, that's what you're doing.
Yeah, this is in a sense this combinatorial people. I mean, this is in a sense their perspective. Yeah. And this is also how I wanted to develop this theory of additive toric varieties. Yeah. Okay, great. Yeah. So back to our example. In type A1. So H goes to C and C goes to P1. So the closure of H is the closure of H inside the closure of C inside P1. So it's just P1. Okay. Now I write P1 as H disjoint union infinity. Just remind ourselves that this H is the H that we started with, and this infinity is what we added when we compactify. Okay, and also this is the alpine stratification of the variety H. H bar. Okay, in this case, H bar is still is smooth, but I suppose that's the only case where it is smooth. So in example type A2, phi plus consists of 3 roots, 2 simple roots alpha beta, and then there's also a positive but non-simple root alpha plus beta. So then our map from H to C to the phi plus becomes H goes to C to the 3rd power, which sends an element x of H to alpha of x, beta of x, and then alpha plus beta of x. Okay, it's obvious that inside C to the 3rd power, the subvariety H is cut out by, if the 3 coordinates of C3 are x alpha, x beta, x alpha, x beta, and x alpha plus beta, then the sum of the first 2 coordinates is equal to the last one. So this is the defining equation of H inside C to the 3rd power. So if you sit down and look at this equation for maybe 5 minutes, you will convince yourself that H bar is cut out by the multi-homogenization of this equation, namely by this. Okay, I won't go into details of what that means. I'll just tell you the final result. So the result is that as a variety, H bar decomposes as follows. There's the finite part H that we started with, and then in the boundary we have 3 irreducible components, each of which is isomorphic to P1. Okay, and these 3 copies of P1 are not disjoint; they actually intersect at a single point, the point infinity, infinity, infinity of P1 to the 3rd power. Okay, and then if I wish, I can decompose this H bar. I have an affine stratification. Oh, sorry. I have an affine stratification of the variety H bar like this, which is obtained by just decomposing each of the P1s into C union infinity. Okay, so in this example, this answers the question by Eckhart. In this example, our H bar sits inside P1 to the 3rd power, but inside P1 to the 3rd power, we have this chart P1 minus 0 to the 3rd power. Okay, I usually call this the infinite chart, and then if you look at H bar inside this infinite chart, it just becomes this quadratic cone xy plus sorry, maybe I don't know how to write it. Xy maybe minus xz minus yz is equal to 0. So it's not smooth at the point 0, 0, 0, which inside P1 to the 3rd power means the point infinity, infinity, infinity. So this is the only non-smooth point of H bar in this case. All right. Okay. Any questions? Okay, nice. Then we move on to the next section. I'll discuss some algebraic geometric properties of the variety H bar. But before that, let me see how much time I have. Okay, I have half an hour. Okay, I prepared a lot, so I'll maybe skip a lot of them. Yes, let's move on to this section 3.2 and discuss the irreducible components of the boundary of H. Okay, so we have seen two examples, type A1 and type A2. In type A1, we've seen that the boundary consists of one point, the point infinity of P1. And in type A2, the boundary consists of three components, each of which is isomorphic to P1. Okay, so the general question I want to answer in this subsection is how do we label the irreducible components of the boundary, and in particular, can one compute the number of irreducible components in the boundary? Okay, to answer that, I need some notation. So I let phi prime be a root subsystem of phi. I say that it's closed if whenever lambda and mu are in phi prime, and whenever their sum is a root, then their sum must be inside phi prime. Okay, so closed means closed under root addition. And then we say that phi prime is good if it is closed and its rank is the rank of phi minus 1, and it's maximal with respect to inclusion among all root subsystems of phi satisfying these properties. Okay, so what does that mean? Back to our examples. If phi is of type A1, then by definition, a good root subsystem has rank 1 less than the rank of phi. Phi has rank 1, so phi prime has to have rank 0, and the only rank 0 root system is empty root system. Okay, so in this case, we have only one good root subsystem, which is the empty root system. And then in type A2, again, phi prime has rank 1 less, so phi prime has rank 1. We have only one rank 1 root system, which is of type A1, consisting of two roots, right? A root and its negative. Okay, so in our case, type A2, we have three root systems of rank 1 less, so plus minus alpha, plus minus beta, and plus minus alpha plus beta. And it's not too hard to verify that these are indeed all good root subsystems. Okay, now you can see, okay, so I remind you that in type A1, the boundary is just a point. It has one irreducible component. In type A2, the boundary is the union of three copies of P1s. So there are three irreducible components. And so magically, the number of irreducible components equal, at least in these two examples, is equal to the number of good root subsystems of phi.
Can you say what is the definition of a root subsystem?
Oh, it's a subset.
Subset, yeah.
Yeah, it's a subset. Which is so okay. Given any subset, you can look at the subgroup of the well group generated by the reflections with respect to elements of the subset. Yes. So you want such a subset to be stable under the subgroup. Yeah.
Okay. So they don't have to be generated by simple roots.
No. That's the point. Yeah. So here you see, this is not generated by a simple root. Yeah. Okay. Nice. Right. So then what I said about components of the boundary is summarized in theorem number 2. So the variety H bar is can be understood as follows. So first, there's of course this finite part H, and then there are some irreducible components of the boundary. And actually, the irreducible components of the boundary are in one-to-one correspondence to good root subsystems phi prime of phi. Okay, and for each good root subsystem phi prime of phi, one can somehow cook up some Cartan H prime of some semisimple Lie subalgebra G prime of G. So this is just a Lie subalgebra. and the irreducible component of the boundary of H bar corresponding to phi prime is the wonderful compactification of this H prime. Okay, so remember, so just to demonstrate what this says. So remember, in type A2, our H bar is H union, H disjoint union 3 copies of P1. Okay, and these P1s are supposed to be these H prime bars. I said that there are 3 good root subsystems: plus minus alpha, plus minus beta, and plus minus alpha plus beta. The 3 components correspond to them. Each of them is a type A1 root subsystem. And remember, in type A1, the wonderful compactification is P1. Right, so these are the H prime bars. Yeah, so that's the content of this theorem. Okay, so in particular, it tells us that in order to understand irreducible components of the boundary of H bar or of H, it suffices to understand good root subsystems. Okay, so then here is an algorithm of how to get good root subsystems. This is an analog of the classical Borel DC benzyl theory. So here I let W be the Val group associated to the root system phi. And then the content of theorem 5 says that up to the action of the Val group W, all good root subsystems can be obtained by the following algorithm. So what you do is you first take a connected component D of the Dinkin diagram of phi. Here I'm just taking care of the case where phi or where the Lie algebra G is semi-simple but not simple. Then for this connected Dinkin diagram D, what I can do is I can affinize it. Okay, so if, for example, type D is of type A, then its affinization looks like this. So this is my D hat. Okay, and in this affine Dinkin diagram, so each node has its Dinkin label. I'll always label the affine node with 1, and all the other Dinkin labels are just the coefficients of the simple roots of the corresponding simple roots in the highest root. Okay, so for example, in type A, the Dinkin labels are all 1. Okay, in type B, almost all the Dinkin labels are 2, except one of them, which is a 1. Type C, the same. In type D, the three nodes on the extreme have Dinkin label 1. All the internal ones have Dinkin label 2, etc., etc. Okay, and then in step 3, what you do is you remove 2 nodes whose Dinkin labels are co-prime. Okay, for example, in my type AN example, I can remove, for example, this affine node and maybe this one. Okay, so then I'm left with a Dinkin diagram of type AN minus 1. And then what I do is I take the root subsystem generated by the remaining, generated by the roots corresponding to the remaining nodes. Okay, yeah, so what this algorithm does is first it adds one root to my one node to my diagram, and then it removes 2. Okay, so altogether it removes altogether the number of nodes in the resulting diagram is 1 less than the number of nodes in the diagram I started with. So the root system I obtained has rank 1 less, which is one of the requirements for a root subsystem to be good. Okay, nice. Any questions so far? All right. And then in general, is H bar smooth? Well, it's not. But there's a very large set over which is smooth. This is the content of Theorem 3. Okay, so remember my H bar in Theorem 2, my H bar is H union H prime bar. Okay, now if I remove the bar from the H prime bar, okay, so I just take H union all the H primes, okay, with no bar. All points inside this union are smooth points of H bar. Okay, so what are the consequences? The consequences are as follows. So the boundary of H has dimension 1 less, at least 1 less. They actually have dimension 1 less, but it's easy to verify that they have dimension at least 1 less than the dimension of H. Okay, but now for this variety, I mean for this open set, we are removing the boundary of each of the H primes, right? So the dimension of H prime is 1 less than the dimension of H. Sorry, 1 less than the dimension of H prime, but the dimension of H prime is 1 less than the dimension of H. Okay, so altogether the dimension of the boundary of H prime, or of the set of points that we removed, is 2 less than the dimension of H. So as a consequence, our variety H bar is regular in codimension 1. Okay, so it satisfies R1. And then combining our analysis of H bar above and the theorem due to Ardila and Booker, one can show that the variety H bar is actually called Macaulay. So in particular, it satisfies S2. So now it satisfies R1 and S2 as a corollary. It's a normal variety. Okay, so why do I care about normality? So let's recall that a toric variety is a normal variety X together. It's a normal variety X together with an action of the multiplicative torus H, such that there's an open dense torus orbit, which is equivalently isomorphic to the torus. Okay, so now what happens for our H bar? So first, as I said, I think of H as an additive group. Now H acts on itself by translation, and this translation action extends to an action of H on H bar. Okay, so now H bar is what? H bar is a normal variety. It has an open dense H orbit, which is just the finite part. And the finite part, of course, is H equivalently isomorphic to the additive group H. So in this sense, by analogy with the usual toric theory, it's reasonable to regard our H bar as an additive toric variety. Okay, so one of the interesting questions I'm thinking about is, can one come up with a definition, an algebra geometric definition of toric varieties, of additive toric varieties, so that our H bar are examples, and these additive toric varieties are classified by some simple combinatorial data, like in the multiplicative case. Okay, if anyone is interested in this, I would be very happy to talk. All right, Then we move on to the final section, computing Betti numbers. Okay, so by theorem 2, I can decompose my H bar as H disjoint union of the boundary components, where the boundary components are H prime bar. Okay, and then I can further decompose each of the boundary components H prime bar using theorem 2 again, right? So each H prime bar then can be decomposed into H prime union some H double prime bar. And then each of the H double prime bars can be further decomposed again by using theorem 2. Okay, so then that each step, what you get is an affine space like H prime, etc., together with some boundary component, and you do this all the way until you have no further decompositions. What you end up with is going to be an affine stratification of H bar. Okay, so using this affine stratification, one can compute the Betti numbers. So let me give you some examples. Okay, so first some notation. So if K is a natural number and G is the algebra I started with, I'll write f of G comma K, or sometimes also f of V, the root system comma K, for the number of codimension K cells in H bar in the affine stratification I just explained. Okay, to explain the Betti numbers in type AN, I'll need to recall the Stirling numbers of the second kind. So these are denoted as capital S of n comma K. These are the number of partitions of the set 1 through n into K non-empty parts. Okay, so for example, if n is equal to 2, okay, so suppose I want to partition into one part, then I only have the set 1, 2. So S2, 1 is equal to 1. Now, if I want to decompose into two parts, I have the decomposition 1, comma 2. So two parts are 1 and 2. So S2, 2 is equal to 1. Now, when n is equal to 3, suppose I want to decompose into one part, I have the decomposition, I have only one decomposition, so namely 1, 2, 3. So S3, 1 is 1. If I want to decompose into two parts, I have 3 decompositions as written. So S3, 2 is 3. And then S3, 3 is 1. Okay, so what we get from this example is that when n is equal to 2, the Stirling numbers are 1, 1. And when n is equal to 3, the Stirling numbers are 1, 3, 1. Okay, but then let's go back to our examples. Where are they? Yes, here. Okay, so in type A1, the number of cells in each dimension are 1 and 1. Okay, in type A2, the number of cells in each dimension are, you see here, there's one 2-dimensional cell, which is H. And then this part, there are 3 1-dimensional cells. And then this part is one 0-dimensional cell, so 1, 3, 1. Okay, so I hope that this is convincing that in type A, the Betti numbers are nothing but the Stirling numbers of the second kind. Okay, yeah, so that's the content of theorem number 6. In type A, and the number of codimension K cells is the Stirling number S of n plus 1, comma K plus 1. Okay, and then we have some classical formulas for the Stirling numbers. which don't look nice. What looks nice is the two variable generating function of the Stirling or of the Betti numbers. Here denoted by f sub a of qt. So I won't go into the definitions. It's just a way to make the things look nice. The corollary is that there's a closed formula for the two variable generating function for the Betti numbers in type A, and it's like it's as written. Okay, and then in other classical types, I can play the same game. It's just that the combinatorics becomes a lot more difficult. For example, in types B and C, I need to consider the so-called Dowling lattice associated to a finite group K. I won't go through the definition of the Dowling lattice. I'll just say that associated to the Dowling lattice, there are the Whitney numbers of the second kind. Okay, here denoted by W, capital W sub K. Okay, then the theorem here, Theorem 7, says that in types B and C, the number of codimension K cells is equal to the Whitney numbers of the second kind of the Dowling lattice associated to which group? To the group with two elements. So the group Z mod 2Z. Okay, and then as in type A, you can write down closed formulas for the two variable generating function. And in type D, you can play the same game. So I'll omit everything. Okay, the natural question is what happens in the exceptional types? So in the exceptional types, can one write down the Betti numbers in some fairly explicit way, or have combinatorists studied the Betti numbers in the exceptional types? Okay, so what happens is someone has to use the language of hyperplane arrangements. So here I'll write a curly A for the so-called Coxeter arrangement. So the set curly A just consists of the root hyperplanes, the hyperplanes in H which are perpendicular to the roots. Okay, and for each hyperplane arrangement, we have its intersection lattice. So here denoted by capital L of A. As a set, the intersection lattice of a hyperplane arrangement consists of just all possible intersections of the hyperplanes. Okay, it's not just a set. It's actually a geometric lattice, whatever that means. In particular, it has a partial order where an intersection X is less than or equal to another intersection Y if set theoretically X contains Y. Okay, so I remark that there's this reversal of directions. This pole set is a ranked pole set. So there's a rank function which is just a codimension. And then in each lattice, we know that there's a meet operation. There's also a join operation. So here the join operation in our lattice is a set theoretical intersection. And moreover, the Val group action on H induces an action of the Val group on the intersection lattice. Okay, so this is just some reminder of classical combinatorics. And then in our situation, geometrically, we have another pole set, namely the pole set whose elements are the cells inside H bar with respect to the affine stratification I just explained. Okay, and this is a partial order because we have the usual partial order where a cell C is less than or equal to another cell C prime if and only if C is contained in the closure of C prime. This pole set is also ranked. The rank of a cell is equal to just its dimension. And the Val group action on H extends naturally to a Val group action on H bar and so this action induces, so there's an induced Bell group action on the cohomology of H bar. Okay, so the reason I introduced the intersection lattice is the following. So we have first this intersection lattice. We also have the pole set, this geometrically defined pole set with respect to our affine stratification. And I have maps F and G back and forth. I don't have enough time, so I won't go through the definitions of these two maps. I'll just say that the content of Theorem 9 is that these two maps F and G are mutually inverse maps that preserve all the structures I mentioned. So they are set theoretical bijections. They respect the rank function, and they also respect the pole set structure, namely the relation less than or equal to, and they also preserve the W action. And so everything is preserved. In other words, to study the geometry of the variety H bar is in some sense equivalent to studying the combinatorics of the intersection lattice L of A. Okay, so using the intersection lattice, I can express the Betti numbers. So what happens is that, so in general, if I have a lattice, here in this definition denoted by L, but I don't think I'll have time to go through this definition. I'll just say the following: for each such L, one can define its characteristic polynomial P of L and its generating function Q of L. And then I define the Whitney numbers of the first kind, denoted by small w of k, to be the coefficient of a certain power of t inside the characteristic polynomial. And then the Whitney numbers of the second kind, denoted by capital W of k, to be the coefficient of the same power of t inside the generating function. Okay, then I guess as a corollary of what I said, and maybe of a consequence of the definition of the Whitney numbers, the number of codimension k cells inside H bar is equal to the Whitney number of the kth Whitney number of the second kind of the intersection lattice. Okay, I don't have much time left, so I'll maybe just mention one interesting phenomenon. Namely, inside my H, I can remove all the root hyperplanes. Okay, so what I get is an open subset of H, which I denoted by M, and I can think of this M as, for example, a complex manifold. Okay, and then you can compute the cohomology of this M. This is done by Orlik and Solomon. One of the results they proved is that, so if you denote by f prime of phi comma k the dimension of the cohomology of M in a certain degree, then f prime is equal to the absolute value of the Whitney number of the first kind. Okay, so our Betti numbers are Whitney numbers of the second kind, and the Betti numbers computed by Orlik and Solomon are Whitney numbers of the first kind. And in a sense, combinatorially, the two kinds of Whitney numbers are dual to each other, maybe related to related by a Mobius inversion formula. So it's interesting to ask what kind of geometric duality is there between our H bar and this M I just introduced that somehow is the reason for this combinatorial duality between their Betti numbers. Okay. Yeah, I don't have time, so yeah, I'll just mention that one can also compute the cup product inside the cohomology. This is theorem 10, the cup product of the cohomology of H bar by using the lattice structure of L of A, and the result is this. Okay, yeah, I'll stop here. Thank you so much.
Okay. All right. Thank you for the talk. Are there any questions in the audience?
I have a question.
Yeah.
Yasu.
Yes, please.
Sure, Anton.
Just I wanted I think I phased out. I missed it. The definition of good subroot system.
Mm-hmm. Yes.
Oh, I see. Okay. Okay. So it's closed is one of the conditions, but not enough.
Right. Also, co-rank 1 is important, and also maximal with respect to both conditions.
Right.
Yeah. Yeah. So, for example, a very good exercise is to try to determine the number of good root subsystems of a root system of type AN. Yeah. The answer is 2 to the n minus 1, but yeah, it's a fun exercise.
If sorry, just a follow up, I guess. What's the so if say a subsystem is not closed, is it true that looking at the map between root system and its dual root system, is it true that if a subsystem is not closed, can we say anything about its dual? Sending roots to co-roots. If one subsystem is not closed, can we say anything about?
Can we say anything?
But the co-roots.
I'm not sure.
Not sure.
I have one example of a non-closed root system here. Yeah. So here in type B3, this phi double prime, so consisting of all short roots, inside phi prime, where phi prime is generated by alpha 2 and alpha 3, is not closed. Yeah,
maybe there's no good answer, or maybe the question isn't well posed, but I just wonder if there's this kind of condition where if one subroot system is not closed, then can we say something about the dual system? Is that one closed?
Maybe in this example, the dual of phi double prime is not closed. That is my impression, but I might be wrong.
Okay. All right. Anyway, thank you.
So do you have any like deformation from the group, the maximal torus compactification to the H bar?
Yeah, I think that's a hidden philosophy. I mean, I learned this from Sam, but maybe he learned it from you. I mean, there's this deformation. Yeah, since you asked it, there's this deformation. So it's a one parameter family of variety of Lagrangian subalgebras, where this one we consider today is the fiber over 0, and all the non-zero fibers are isomorphic to this plane started by Evans and Lu. And I suppose if you take H bar inside here, it goes to the H bar that we studied today. I mean, thank you for your question.
Okay, thank you. Okay, and any other questions? Okay, if not, let's thank the speaker, Li Yu.
Thank
Really
you.
nice talk.
Thank you.
Thank you. Okay, so thanks to everyone for coming. So next week it'll move to the normal European, I mean the normal, the other time, which is like,
Western hemisphere.
oh, actually next, isn't the time has changed, right? The time
Yes, it
clock
happened on Saturday, but yeah.
already changed.
Yeah.
Ah, okay.
Yeah.
All right. Okay. Okay. Thanks to everybody.